Welcome back to part 2 of section 1. Here we're going to continue looking at those parametric equations, but in this one we're going to see how we can do calculus with them. So here we go.
To start out, let's look at the derivatives of a parametric equation. So if we have a parametric equation, this is just a random parametric equation, we could take the derivatives of each side. We could do it implicitly to get something like dx equals 4 dt, dy equals 2 cosine t dt. We could have also gone with the derivative of x with respect to t, dx over dt equals 4, and dy over dt equals 2 cosine t. It doesn't really matter which way you do this, but what we're looking for is the derivative has always been dy over dx. It's the change in y over the change in x. That's the slope. And so if we wanted to know dy over dx, well, we have dy, we have dx, we just plug them in there. 2 cosine t dt over 4 dt. The dt's cancel. Everything will have a dt in it. They will always cancel. And we're left with 2 cosine t over 4, which could just, in this case, reduce to 1/2 cosine t. If we were to do it the other way, where we had dx over dt and dy over dt, we would still divide exactly the same. We have dy over dt over dx over dt, which when we divide by fractions, this would be dy over dt times, flip and multiply, dt over dx. Once again, dt's cancel to get dy over dx. So to find the derivative of parametric equations, we just find the derivatives of each of them individually and put the y over the x. Now that's the trick. Just like finding slopes, a lot of times people try and go x over y. But remember, it is rise over run. The y is the rise, the x is the run. So let's look at another one. This graph is the graph of an ellipse. Specifically, we have 4 here, which means we're going to go out 4, back -4, and the 16 here tells us we're going up 16, down -16. There's no addition or anything there that's going to move the center. That you'd have to have like a 4 cosine of t plus something. And so we get an ellipse centered at 0, 0 with, yeah, it doesn't look like an ellipse, but you get the idea. You get an ellipse centered at 0, 0, where the 4 would be the horizontal radius, the 16 would be the vertical radius. Those aren't technically radii, but it's how far over we go and how far up and down we go. Things to remember from an ellipse from pre-cal and even honors algebra 2. The long axis is the major axis. The short axis is the minor axis. The vertices are at the end of the long axis. In this case, they'd be the y points. The co-vertices are at the end of the minor axis, the short axis. Those would be the x points, the -4, 0, and 4, 0. There are a couple foci in there, but we don't need to worry about finding those. The equation, if we wanted to make this into a normal equation, it's x squared over this 4 squared, which is 16, plus y squared over 16 squared, 256, equals 1. So that's the regular equation that we'd have for this particular ellipse, but that changes into here. It's kind of like a circle, except these two numbers aren't the same. So let's find the derivatives of these so we can see the slopes of the line. So dx, we'll just go dx over dt equals the derivative of 4 cosine t. The cosine will give us negative sine, so we'll have negative 4 sine t, and dy over dt, the sine will give us cosine, so we'll get 16 cosine t. We'll go y over x, so dy over dt, or dy over dx, equals 16 cosine t over negative 4 sine t, which will be, that'll be a negative 4. Cosine over sine is going to be cotangent t is going to be the derivative of this. Now, one of the things it'll ask is when will there be horizontal or vertical asymptotes? Now, a horizontal asymptote is when the slope equals 0, if you remember back from the beginning of the year, and a vertical asymptote is when the slope is undefined. So, in cotangent, which is cosine over sine, when does it equal 0? It equals 0 when cosine equals 0. So this will have a horizontal asymptote at t equals, when cosine equals 0, that's going to be the pi over 2s. It's when it's vertical. So this will be a pi over 2 and 3 pi over 2. And a vertical asymptote at, that's when the sine equals 0, which will be at 0 and pi. Which, being that we start here and we work our way around, this would be 0, it's horizontal, pi, it's horizontal, pi over 2, it's vertical, and then pi over 2 and 3 pi over 2 is horizontal. So it matches what we see with the graph here, but you might not be looking at a graph at the time. However, you can find when things are 0 and things are undefined. We've been doing that for quite a while. The only thing new is how we get that derivative. And so, the derivative for parametric curves is exactly what we're talking about. It's dy over dx, which this is the other way of writing it. This would be another way if you went for x was f of t and y is g of t. And then it is important that the denominator doesn't equal 0 because that would be undefined. So the derivative doesn't exist. We know it happens. It's a vertical line, but technically the derivative doesn't exist. So that's how you find a derivative of a parametric equation. Next, we'll go for arc lengths. So when we're talking arc lengths, we split this up and we can look at these. We can zoom in and we get this length, which is the hypotenuse of Pythagorean, or hypotenuse of a right triangle. And so it's the square root of the change of x squared plus the change of y squared. But we want to get it to be teeny tiny, so that the smaller it goes, is the limit as these 2 points go to 0, will give us the actual thing. And so that change in x and change in y, that itty bitty change, is going to be the derivative. And then we have all of these that we need to add up. And so we're going to have to take the integral the antiderivative from this point to this point of this, where these guys inside are the derivatives. Yes, we're going to have a derivative squared plus a derivative squared square root, then we're going to take the antiderivative of that to give us this equation. It'll be fun. So let's plug stuff in. And really all the rest of this is just plugging functions into this equation right here. This is the last actual piece. It's just plugging things in. Being that the simplification of this could be sometimes tricky, practice is going to be important. Not quite as much as last chapter, but you're going to want to do enough that you remember this equation, because, I mean, it just rolls off the tongue. So let's look at a couple problems. So because you have already forgotten what that equation is, let's throw it up there so that we can see it. So let's do the circumference of a circle. Why not? The circumference of a circle. Why is it 2 pi r? Yes, 2 pi r. Sorry, I almost said r squared there, thinking area. Why is it 2 pi r? Because we said so? Because we cut a circle and stretched it out? It's really hard to find the circumference of a circle in just regular function geometry because it's not a function. But being that a circle can easily be described with parametric equations, we can find the circumference of it. So the circle, it's going to be x equals a cosine t, y equals a sine t, where a is the radius. Notice, remember the ellipse? Those two values were different. It was a and b. And then t will go from 0 to 2 pi. So we're going to have dx over dt is going to be, so a cosine will give us negative sine. So that'll be negative a sine t. And dy over dt will be a cosine t. And so we're going to have the square root of negative a sine t squared plus a cosine t squared. We're going to take the antiderivative of that from 0 to 2 pi, and that will equal the circumference. Now, there will be times, even in the assignment, that you're not going to be able to find the antiderivative really. And in those questions, it'll say approximate the antiderivative, but simplify it as much as you can first. In this one, we can actually find it. So the first thing is we will square the two deals. That gets rid of the negatives. We just have a squared sine squared t plus a squared cosine squared t. I guess we have a dt back here. So the circumference will equal, we can factor out that a squared, 0 to 2 pi, square root of a squared, sine squared t plus cosine squared t dt. Sine squared of something plus cosine squared of something. Doesn't that sound familiar? It's the Pythagorean identity. We used it in the last section too. If you remember, and you were in my pre-calc class when we were really going over these, I mentioned that the Pythagorean identity with a couple of the other basic identities will get you through pretty much all of trig. Here it is again. Sine squared plus cosine squared equals 1. So that can basically just go away because 1 times a squared is just a squared. What's the square root of a squared? It's a. So here the circumference will equal 0 to 2 pi of a dt. A is a constant, like say 2, what's the antiderivative of 2? That would be 2t. So here we'll get at from 0 to 2 pi. Plug in 2 pi minus plug in 0. We get a times 2 pi minus, doesn't matter because it's going to be a times 0, which is 0. So the circumference is a times 2 pi. 2 pi times the radius. And so we get the circumference of a circle. Yes, we knew that was going to be the circumference before we ever started, but isn't it kind of fun to see it? So let's do another one. This one we don't know what it's going to be right away. And it's also not a formula. We'll actually use some equations. Let's find the length of the hypercycloid, otherwise known as an asteroid. So we have x equals cosine cubed t, y equals sine cubed t, and we're going from t equals 0 to 2 pi. So the first thing we want to do, I'll change color here so we can see the difference. We're going to find our dx and our dy. Dx over dt, so we have cosine cubed t, that's going to be something cubed, so we'll have 3 times the something squared, times the derivative of the something, which will be a negative sign. So we'll go sine t, we'll put the negative out in front. And then dy over dt is, so y is sine cubed, so we'll have 3 sine squared t times cosine t. Now we need to put these into our equation. So the length is going to be the antiderivative from 0 to 2 pi, because that's given right there. And then we'll have a square root of the dx over dt squared. So that'll be negative 3 cosine squared t sine t squared plus 3 sine squared t cosine t squared. We can square each of the things. Giving us a square root. It'll be 9. Cosine squared becomes cosine to the 4th t, then sine squared t plus 9 sine to the 4th t cosine squared t. I don't know why I have parentheses there. It just happened. The 9s we can factor out. We can actually factor it out, square root it to get 3, then move it out in front so we don't even have to look at it. So let's do that. We'll get 3 times the antiderivative of 0 of 2 pi. Now we don't need to worry about the 9s. So each of these has a sine squared and a cosine squared. So let's factor out a sine squared cosine squared from each of them. We'll have sine squared t cosine squared t. So times what's left in the first one will be a cosine squared t plus what's left in the second one will be a sine squared t dt. Oh, hey, look, Pythagorean identity again. Weird how that keeps coming up. So that's just one, it goes away. So we have the square root of sine squared plus cosine squared. Both of those are squared, it's multiplication. We can take the square root of each of them. So we get L equals 3, 0 to 2 pi of sine t cosine t dt. And now we can actually find the antiderivative of this one. So I would let u equal sine t. Oh yeah, u substitution. You knew it was coming eventually. Du will equal cosine t dt, which means we have du right there, u. So this is just going to be L equals 3 times the antiderivative of u du, which will be 3 times, that'll be 1/2 u squared, which we can substitute back in. U as sine. So it'll be 3 times, well, let's go 3/2 times sine of t from 0 to 2 pi. If we plug in sine squared of t, if we plug in 2 pi, sine is going to be 0. If we plug in 0, sine is going to be 0. So that doesn't work because we're going to have the positive and the negative cancel itself out. So we'd want to split this up into a few pieces. We can go from, I'd go from 0 to pi over 2, and then pi over 2. Then you could actually multiply by 4 because these are going to be symmetric. So let's erase some of this other one so that we can continue this. You guys all have this in your notes. If you don't, you can go backwards. If I can actually erase, there it's going. You can go backwards and get back to that. If I could erase, come on. That'll be enough. So, taking this up over here, we're going to have 3/2 times 4 sine squared t from 0 to pi over 2. Now we can plug in pi over 2 to get 1, minus plug in 0 to get 0. 3/2 times 4 is just 6, so we have 6 times 1, which means that the length of this particular hypercycloid is 6. Is it coincidence that it's 2 times that distance 3? I guess you'll have to find out. So, as you're doing that, keep working problems, keep asking questions, and as always, happy mathing.